Okay, so we have just really focused on this term, sum of squared deviation scores. So we got the deviation scores, we squared them, and then we summed them and got 10 points. And then we averaged that and got 2 points. Now remember what our goal was. What I said we wanted to find out was what is the average distance of the raw scores from the mean. Well, I'm not there yet. Why? These are the distances, but I squared them. So what I really have is the average squared distance of the raw scores from the mean. This is a measurement of variability called variance. So variance is a step along the way to getting done what we say we want to do. Variance is also a measure you're going to have all semester long, particularly used in inferential statistics. So for us right now, we're still mainly focused on descriptive statistics. Variance isn't something we would use much other than a step along the way to get to where we're going. But in inferential statistics, it's something that you'll be dealing with, calculating and conceptualizing forever in this course. So variance is what I just basically said. Variance is the average squared distance of raw scores from the mean. What we really want is the average distance, but what we have in variance is the average squared distance of raw scores from the mean. And we learned that that is a 2. The average of the squared distances was 2. Okay. What we're ready for now then is to go right back through the same example, but do it the way we actually want to do it, so we don't have to go through these dead ends. This is a method that you can use. Again, your author explains this to you. A lot of students are drawn to it because it looks pretty straightforward, and it is. The problem is that doing it this way, getting to our variance this way, is messy if the data has any decimals in it or everything doesn't work out exactly even. We're using nice, clean, simple whole number examples here. You could do it this way. But as soon as the data has any time, if the mean was 3.26, all the deviation scores would have decimals in them and the squares would have decimals, and this becomes very cumbersome. This is what your author calls the definitional approach. In other words, doing it this way at least looks like we're doing what we're talking about doing. What we want to do instead is what's called the computational approach. That approach we just did looks good on paper, but your calculator doesn't like it much. So how do we get the same job done, but using our calculators? Well, let's start with, we need some notation. What's the symbol we're going to use in statistics to denote a population variance? Remember, we're only talking about populations. The symbol is this. This thing on the left is another Greek letter. I mentioned to you before that at this point in the course, whenever we see Greek, we know we're talking about populations. And this is a lowercase s. Sigma is a capital S for the Greeks. This is a lowercase s. And it's got an exponent on it. That's part of the symbol. That's not an instruction. That's just part of the symbol. Think about what the definition is. Variance, again, variance is the average squared distance of raw scores from the mean. So we put a square on the symbol to remind us that our measurements have been squared in this. So to calculate variance the effective way, the efficient way, we do it in 2 steps. The first thing we do is we calculate what's called the sum of squared deviation scores. That should sound familiar because I said that a whole bunch in the previous video clip. Sum of squares, this is the sum of squares. We still need to get that. We still need to get the sum of squared deviation scores. We just don't want to do it the way I showed you initially. The way that's more effective with a calculator is this. So first of all, it has its own symbol. SS is sum of squares. Officially, again, it's sum of squared deviation scores, but we usually just call it the sum of squares because it's faster and we're lazy. So to calculate that, here's what we need to do. Get the summation of the squared raw scores. square the raw scores and add those squared values up. And then we're going to subtract from that the summation of raw scores, and the summation has been squared. So here square then add, here add then square, and all that divided by the number of scores in the population. Okay, so what we need to do then is just take our order of operations and work right through it. So this says that I need to square the raw scores. So I'm going to need to get a column for squared scores. Well, 5 squared is 25, 4 squared is 16, 3 squared is 9, 2 squared is 4, 1 squared is 1. And then this says sum up those squared raw scores. So I need to add these up. Again, I recommend you take a quick pause here, grab your calculator, and see what you come up with. 25 plus 16 plus 9 plus 4 plus 1. And speaking of calculators, let me grab mine. So 25 plus 16 plus 9 plus 4 plus 1. 55. Now, let's look on the other side. And on the numerator, it says add up all your raw scores and then square that summation. So 5 plus 4 plus 3 plus 2 plus 1, 5, 10, 15. So this is 15. Now we just plug in to the formula. So the summation of squared raw scores was 55. The summation of scores is 15. We need to square that and then divide by how many scores do we have? 1, 2, 3, 4, 5. So square your 15 and divide that by 5. So 15 squared, 15 squared, 225. 225 divided by 5 is 45. 55 minus 45 is 10. Now look back at your notes when we did this the first time, the long way, the wrong way. And at the bottom of that, you saw that the summation was 10 points. The sum of squared deviation scores is 10 points. We just got it a different way. We got it with this formula instead of the other approach of getting all the deviation scores and then squaring them and then summing them. Again, this way works better if we don't have conveniently all whole number data. It's faster, it's more efficient. And you'll be dealing with this again on and off much of the semester. So just get used to this approach. So now we have the sum of squared deviation scores for 10 points. Now, the second step is to compute variance itself. Population variance. So remember what I've been telling you. Don't call it the name of the symbol. Don't call it S squared or little sigma squared. Actually, students are more likely to call it O hat squared or something like that. This whole symbol, its name is population variance. Trust me when I say that students who don't practice saying what the term is eventually get lost. You're going to have so many symbols in this course down the road that if you're not using the vocabulary, you just get buried in it. You don't really remember what that is. But if you say population variance, you know what you're dealing with. So we can see all we've got to do. It's very simple. It's just division. We're just kind of doing the averaging part. So our sum of squares was 10 points. Our number of scores is 5 points. So the population variance is 2. Remember, we saw that again on the other way of approaching this. So the average squared distance of the raw scores from the mean for this data is 2 points. Now that isn't the promised land we were trying to get to of the average distance, but now we're in position to do that for the next piece. So with this, we have population variance complete. We do it in 2 steps, sums of squares, then compute the variance. All right, so we'll continue forward in this on the next clip.